Okay, so we designed the first order filter, which is RC filter. And the procedure to do that, we have to select these components and the devices. So what we do is we go to component library and then we look for the voltage source. We type the voltage and here the source comes. We select this, click OK, and there is how the source comes. We place it on the screen, then right clicking it will open this property of this voltage source. We click advance and now we want to analyze the frequency response of this circuit. So what we do here, we have to select an AC amplitude, which is 1, AC phase, let's say 0, or can be left blank. We can include series resistance and parallel capacitance to make it more real or a practical voltage source, but for now we just leave these fields blank, and then we click OK. So you see now this voltage source is ready, and after that we can actually move it to the location we want. So I press escape now, so just to show that how we have done the voltage source. So I cut it. Now next component is to select the resistor from the toolbar. We see that resistor R. Right clicking it will give me the value. For example, I choose 1.5 kilo ohm and then the value will come here. Similarly for the capacitor, I click the toolbar, then right clicking the component will give you the value of capacitor. So I write 1 microfarad. So here it reflects here. So this is how I choose the components and the devices, including voltage source. And by clicking in their properties, one can select the proper values. So I delete them now. And then through the net connections, I connect all these components together. And this is the circuit which is called as RC circuit. And now the values are given, we'll know that what value it is and why those values are selected. So for example, if we want to, let's say I want to design a filter circuit, first order, passive, using passive components. So you see the problem statement is if you are asked to design the circuit first order using passive components, so we can actually design it as shown. So now next step is to do a simulation. So for the simulation, we click the button simulate and we don't press run because we haven't mentioned what command, what analysis we want to do. So we click edit simulation card. Here you come and you see the AC analysis tab has already been selected because you have mentioned the AC source there. Now you what AC analysis does is that it will compute the small signal AC behavior of this RC circuit. It will first compute the DC operating point. We have seen in the previous model what is DC operating point and how to do that analysis. Then in the AC analysis, you can choose the type of sweep. For example, octave or decade or linear or list. This basically tells us how the frequency will be swept, and a node voltage as a function of frequency can be plotted. So for example, we select decade. So it means it will start from the frequency 1, start frequency is 1, stop frequency is, let's say, 1 megahertz. Okay, because here in this frequency range, we are expecting the behavior of this circuit. So a number of points per decade are given as 100. We can have 1,000 also, we can have 10, or for example, we have taken it 100. And decade means it will start from frequency 1 hertz, and after 10 hertz, every 10 hertz, the data will be plotted. For example, if you want to compute the output voltage of the circuit with respect to frequency, it will compute accordingly. So you see the syntax, if we write the spice netlist, the syntax is dot AC. In the options are octave, decade, or linear, and then number of points, then start frequency and the end frequency. And this is how the command will look like if we generate the spice netlist. We'll see that in a moment. So for example, I have now in the up here, we see that dot AC decade, number of points are 100, starting frequency is 1 hertz, and end frequency is 1 megahertz. And we can also go to view and click spice netlist. So as explained before, see how the spice netlist is generated. Is basically tells us the interconnection of components. So it says that you have chosen resistor R1, which is connected between node A and node out. It has a value of 1.591K. It has a tolerance of 1% and a power rating of zero point 0.1 watt. Similarly, you have a voltage source. It is connected between nodes A and 0, which is ground. It is AC voltage source with a magnitude of 1 volt and phase is 0. Now capacitor C1 is connected between two nodes, which is out and ground. You can also refer to the schematic. It has a value of zero point 0.1 microfarad. It has a voltage rating of 16 volt, and there are some other parameters. For example, the current RMS, series resistance of the capacitor, inductance of the capacitance. So it is making the capacitance a more practical capacitor. Similarly, for the resistors, you can also see those property by right clicking these components. Then command is, it is a RC circuit, and we mention the analysis to be performed. So for example, dot AC decade, it means how the frequency sweep will be done. 100 points between start frequency of 1 hertz to end frequency of 1 megahertz. And that's the command, that is design a filter circuit of first order using passives. Back anno dot back anno is basically a command which will annotate the voltages, node voltages, which we can print and reflect on the schematic. Dot end ends this spy script. So this is how you can actually generate this spy script. So one way is to design an electronic circuit is to draw the schematic and uh, refer to the library of components and put it them, place them in the screen and connect them, and then do some analysis to see the response. Another way is to have a text-based netlist. It's called a spice netlist. We close it. So right clicking it shows that register value, the tolerance, and zero point 0.1 is the power rating. We can also click the select register. You can see that I have selected this register from the library. So it has all the properties, power rating already mentioned. Similarly, for the capacitor, I select the value of capacitance, voltage rating, RMS current rating is 0, and equivalent series resistance of this capacitor is 11 ohm, and rest parameters are not mentioned. So I have selected this capacitor from the library. So you see that in the library, this is a part number, manufacturer name is mentioned, and its properties. So it's a real model of a capacitor that has been used in the schematic. Once that is done, we can actually see how this circuit will behave. So we are interested in plotting this output voltage, that is the voltage across the capacitor with respect to ground. So before that, the RC filter will be designed in this way. Suppose we are given the frequency of this RC filter is called as cutoff frequency. All right, so this is the cutoff frequency, or also called as role of frequency, we'll see that the response of the filter, that is the output voltage divided by input voltage, that is a magnitude. Okay, it behaves something like that, and this is the frequency omega, or you can say 2 pi f. So if we are asked to design an RC filter for a frequency of 1 kilohertz, what we can do, we can refer to this formula. So we choose the value of a capacitor, for example, 0.1 microfarad. And for that value, we can plug in those values of capacitance and frequency and compute the value of R, which comes out to be 1.59 kilo. And that's how what we have done here. So you see, R1 was calculated for a given value of frequency. We chose the value of capacitance to be 0.1 microfarad, and we calculated the value of resistor to be 1.59 kilo. So again, AC voltage of 1 volt is applied. Capacitor of 0.1 microfarad was chosen for a design frequency of 1 kilohertz. We use this formula, that is C equal to, for C equal to 0.1 microfarad, and frequency, design frequency of, let's say this is FC, or cutoff frequency of 1 kilohertz. So we have R comes out to be 1.59 kilo ohm approximately. So let us simulate the behavior of this circuit. So what we do here is that we'll just run the analysis and we'll see how the circuit behaves. So we go to simulate and click run. And now the question is that we have to understand, we have to plot the response of this circuit. So we'll see how the circuit response looks like. So what we do is that we have run the analysis and we click the node out right here. And here is how we get the plot. So this is an output voltage response with respect to frequency. X-axis is the frequency, y-axis is the output voltage, magnitude of it, and we then take a dB. We can right click the y-axis and we see the range of the y-axis from 0 dB to minus 66 dB. We can alter here, and it has a stop of 6 dB. For every 6 dB, we have the tick. So we can also have this response to be linear. So we click here and we see that how the voltage will vary if we choose the linear scale of y-axis. Again, I right click on the y-axis. I choose the decibel because that's how I want the magnitude. I can also click the don't plot the magnitude option here. So doing so will not plot the magnitude, but we'll just see, we have to plot it. So again, so now here we need to see, on the left side is the magnitude, on the right side is the phase, how the phase of the circuit varies. So phase variation is from 0 degree to minus 90 degree, and we now have to see, understand this frequency. So see, the gain is constant up to certain frequency. So if we choose the minus 3 dB point, for example, I right click on the V out, and here it is, and I attach a cursor. First click OK. Now here I am on the cursor, so I can left click this cursor and see how it varies. So basically I don't want two cursors, so we'll just remove that again. We'll see that the first cursor is here and how it varies. So you see, now I am just clicking, selecting the cursor and varying it. So I go to minus 3 dB point. For example, right here, I select. So now here, what is to be noted, for the For the minus 3 dB point, the frequency is about 1 kilohertz. So which is what we define, what we designed the circuit for. So this is the cutoff frequency at minus 3 dB point, and at that the phase is approximately minus 45. So right here the phase is minus 45. So you can click here. For example, you click, the phase, and see, you see here right now we are at exactly minus 45 degree, and the phase is varying from 0 degree to minus 90 degree. So that's how we have designed this filter. It is also called as single pole filter. This is called as single pole filter, and this is the pole of that filter, approximately 1 kilohertz. So this is how we can actually design the circuit. If you right click the phase, we'll see what it gives us. So if you right click here, we have this right vertical axis, and the phase variation is from minus 0 degree to minus 90 degree. We can select don't plot phase, and this is how the screen will look like. Okay, so this is all about your circuit diagram, designing the filter circuit, and this is how we actually do that.